Today we're diving into a paper that explores the use of artificial intelligence to automate scientific discovery. The paper, SciAgents, Automating Scientific Discovery Through Multi-Agent Intelligent Graph Reasoning, proposes a system that leverages large language models and ontological knowledge graphs to generate and refine research hypotheses. What are the key challenges that this paper addresses?
The paper tackles the limitations of traditional human-driven research methods, which are often constrained by the researcher's ingenuity and background knowledge. It also addresses the challenge of exploring the vast amount of existing scientific data to extrapolate knowledge towards entirely novel ideas, particularly in multidisciplinary areas like Bioinspired materials design. So how does the system, SciAgents, aim to overcome these limitations?
SciAgents utilizes three core concepts. First, it employs large-scale ontological knowledge graphs to organize and interconnect diverse scientific concepts. Second, it uses a suite of large language models, LLMs, and data retrieval tools. And third, it incorporates multi-agent systems with in-situ learning capabilities.
Can you elaborate on how the knowledge graph plays a role in this system?
The knowledge graph serves as a foundation for the system's reasoning capabilities. It provides a structured representation of scientific concepts and their relationships, allowing the system to identify connections that might not be immediately obvious to human researchers.
And how do the LLMs contribute to the process?
The LLMs are used for various tasks, including generating research hypotheses, expanding on existing concepts, and critically reviewing the generated proposals. They are trained on vast amounts of scientific data, enabling them to understand and synthesize information from diverse sources. The paper describes two distinct approaches for generating research hypotheses. Can you explain the differences between these approaches?
The first approach involves pre-programmed interactions between agents, following a predefined sequence of tasks. This approach ensures consistency and reliability in hypothesis generation. The second approach features fully automated agent interactions, where the order of interactions is not predetermined. This provides a more flexible and adaptive framework that can dynamically respond to the evolving research context.
The paper focuses on the application of SciAgents to biologically inspired materials. Why is this area particularly well suited for this type of AI-driven approach?
Biologically inspired materials design often involves drawing inspiration from nature's toolbox and applying those principles to engineering applications. This requires a deep understanding of diverse concepts and relationships across multiple disciplines, making it a challenging task for traditional human-driven research methods.
The paper describes a process that starts with keyword selection and culminates in a detailed research proposal. Can you walk us through the key steps involved?
The process begins with the selection of keywords, either by the user or randomly by the system. These keywords are then used to generate a knowledge path within the ontological graph, which represents a series of interconnected concepts. This path is then analyzed by the system's agents, who generate a structured research proposal that includes a hypothesis, expected outcomes, mechanisms, design principles, unexpected properties, comparisons, and novelty.
The paper highlights the importance of critical review in this process. How does the system incorporate this aspect?
The system includes a dedicated critic agent that thoroughly reviews the generated research proposal, summarizing its key points, highlighting strengths and weaknesses, and suggesting improvements. This critical review process helps ensure that the generated hypotheses are scientifically sound and feasible.
The paper also discusses the use of external tools, such as the Semantic Scholar API, to assess the novelty of the generated hypotheses. Why is this important?
Assessing the novelty of a research idea is crucial to ensure that the system is not simply replicating existing work. The Semantic Scholar API allows the system to search for related publications and determine whether the generated hypothesis is truly novel and contributes to the advancement of knowledge.
The paper demonstrates the system's ability to generate diverse and novel research hypotheses. Can you provide some examples of the types of hypotheses that were generated?
The paper presents several examples, including a hypothesis for developing biomimetic microfluidic chips with enhanced heat transfer performance, a hypothesis for developing a collagen-based material with a hierarchical, interconnected 3D porous architecture, and a hypothesis for developing a novel biomimetic material by mimicking the hierarchical structure of nacre and incorporating amyloid fibrils.
The paper concludes by discussing the potential impact of this AI-driven approach on scientific discovery. What are the key implications for the future of research?
The paper suggests that AI-driven systems like SciAgents have the potential to significantly accelerate scientific discovery by automating the process of generating and refining research hypotheses. This could lead to breakthroughs that might otherwise remain undiscovered, opening new avenues for exploration and innovation across various fields of study.
The paper also highlights the importance of ongoing research and development in this area. What are some of the key areas for future work?
Future work could focus on expanding the system's capabilities by incorporating agents that can conduct experiments or solicit data from simulation studies. The modular approach of SciAgents provides a flexible framework for integrating these additional functionalities.
This was a fascinating discussion on the potential of AI to automate scientific discovery. Thank you for sharing your insights.